This class is about aluminum, and in particular we will focus on the Madder Lake and its identification using aluminum. Aluminum 13. Aluminum can be identified by its K-alpha line at 1.5. Since the energy is so low, of course we need to check if about 1 centimeter of air puff is too much for this low energy photon to reach the detector. So we use our calculator, online calculator, we put the energy 1.5, 10 millimeter, and we get that the transmission is almost 25%. So we have a decent amount of these X-ray lines from aluminum that can reach the detector. As usual, we want to have a baseline, so we tested a cube of pure aluminum, and we get this peak, so it's at 1.5, and we have a count of about 20,000. It's a good count compared with the other lower atomic number element. Now we wanted also to test as a baseline alum, which will play an important role. So here we have a piece of a crystal alum. Alum is a potassium aluminum sulfate. The concentration of alum is less, and indeed the peak of aluminum in alum is much less than the pure cube metal, so we are in the order of 1000 counts. Madder Lake, as well as the other lake, are produced by precipitating a colorant in the flowers and the roof of some plants or other part of the animals like insect, like in the case of cochineal. So basically this organic colorant molecule is precipitated with a salt called a mordant. So in general, most common was aluminum potassium sulfate. And Madder Lake indeed was made with this mordant, so often aluminum is a signal, a line that we expect when observing Madder Lake. For this experiment, though, we tested this set of Madder Lake version made by Kramer. So these are different kind of Madder Lakes, so Madder Lakes made with different recipes. We applied Madder Lakes test samples into this cardboard, and we analyze with the XRF spectrometer. This is the result for 37202, the one up here. Of course, since we are interested to the signal of aluminum, we collected the spectra with the no filter setup. We see the peak of aluminum over here, and also we see the peak of potassium and calcium. So this one is let's say, the more common spectrum that we get when analyzing Madder Lake. We can find aluminum and potassium, indicating the use of a alum, so potassium, aluminum, potassium sulfate as mordant. Though Madder Lake can be done with different solutions. In this example, we have here the previous Madder Lake, the aluminum potassium based Madder Lake, and on top we have a sample 37203. In this case we see the peak of tin over here and chlorine over here. This is because in this case was used a salt of tin and chlorine. So basically it will be a stannous chloride or a stannic chloride. This sample, the 37217, this one is a Madder Lake much darker tone. This formulation was not really used for paintings, but actually it's used for wood, in particular for instruments like violin, to give the darker tone to the wood of this instrument. It is achieved using now not aluminum salt but iron salt. We see the calcium and we see calcium over here, and much important, a lot of iron in this formulation at 6.4. Sample 37218 show a lot of phosphorus over here and also some calcium. This could indicate the use of bone ash calcium phosphate, which was rare as an application, but still could be the case. This is the explanation for all this phosphorus and all this calcium over here. This sample and this other sample shows an important content of sulfur, other than potassium. The strong content of sulfur could be related to sulfuric acid that in relatively modern formulation were used to enhance the extraction of the colorant, so we could have it as a residue from this process. Last example show a content of copper. This is because in this case as a mordant it's used a copper sulfate rather than an aluminum sulfate, potassium sulfate of the iron sulfate that we saw before. So another metal like copper can be used, and in this case we have the Madder Lake containing a lot of copper.